This video will explain to you how to do so-called boat problems or airplane problems. I will begin with a boat and we'll extend it to airplanes after that. First of all, if I have a river, say that the river is flowing, these are the banks of the river, and the current is in this direction, I'll call that BC. Now, if I have a boat that's capable of traveling at a certain velocity in still water, and I will call the velocity of the boat VB. And the boat heads straight across the river from this bank to the top bank. Now, what we'd like to calculate is the actual speed of the boat as it crosses the river. Let us try to suppose that the river is 65 meters wide. So how fast will the boat actually be moving across the river? Now remember, there is a current pushing it to the right, and so as we draw the diagram, this is the velocity of the boat, and then tip to tail, I'll draw the velocity of the current. And so my velocity that the boat actually takes would be along this path. So this is the actual velocity of the boat as it crosses the river. And it produces an angle here from straight across the river. Or you could use beta, which is 90 degrees minus theta. So, to find the actual velocity of the boat as it crosses the river, the actual is equal to, using the Pythagorean theorem, the square root of the velocity of the boat in still water squared plus the velocity of the current squared. And that would be the speed. To find theta, we would use inverse tangent of the side opposite, which is the velocity of the current, divided by the velocity of the boat in still water. So that beta is 90 minus theta. And when you give your actual velocity, you would say that it is the magnitude, and your direction could be given as beta degrees from the bank. Or you could have given it as theta degrees from straight across. Now, I'm sure you've all experienced situations where you've been in a river or something that is flowing, and you're trying to move in one direction and the current is pushing you in the other. Another example where you'll notice this in everyday life would be when a bird is trying to fly and there's a crosswind. His little head will be pointed in one direction, but he'll actually be moving at an angle to that, just like the red actual velocity of the boat is in this diagram. Now, another situation might be if I still have this river and my current is still in this direction, and my velocity of the boat in still water is about the same length, let's say VB, and I know the width of the river. I believe we said 65 meters in the one before, so we'll keep it the same river. Now my boat heads straight across the river. That's the speed of the boat in still water. The current pushes me this way, and so my actual velocity, just like before, is going to be here. Now, I can also calculate the time that it takes to get across the river. Time to cross river. The key here to remember is the distance across the river is straight across, and the velocity in the same direction is the velocity of the boat in still water. So what I'm going to have to do is say V equals D over T, and in this case it will be the speed of the boat in still water is equal to the width of the river divided by the time. Since I'm solving for time and it's in the denominator, the first thing I'm going to do is multiply both sides by T, and then I'll divide by the speed of the boat in still water. So if I want to find out how long it takes me to cross the river, I would divide the width of the river by the speed that the boat is capable of going in still water. Now, another thing that is often asked is the distance boat ends up downstream. Now, by the distance the boat ends up downstream, if he's heading right here, you can see that this path is going to take him here. So this would be the distance that I'm looking for right here. The distance off of straight across to where he actually ends up. And so this would be my distance, and I'll just say D for downstream. As you can see, that's in this direction, so the velocity that's in the same direction is the velocity of the current. And those two always have to be lined up. With whatever distance you use, you have to use the velocity in that same direction. So the velocity of the current is equal to the distance downstream divided by the time. So the distance downstream is equal to the speed of the current times the time. Now the time that you're being pushed downstream is also the time that you're going across the river, because you're moving across the river and being pushed downstream simultaneously. Rather like with projectiles, when you're moving horizontally, you're also moving vertically. So this would be the way that you would solve for the time it takes to cross the river over here, and then on this side shows you how to find the distance the boat ends up downstream. The previous slide showed you how to determine the actual velocity of the boat along the path that it follows. Now, our next example could be how far or what angle should you head your boat if you wanted to actually end up straight across the river. So we'll still use our same river, 65 meters wide. Our current is still in this direction, and our boat speed is still going to be the same resultant vector, or the same length vector, I should say. Now, in this situation, I want my actual velocity to be straight across, because I want to know how I need to guide my boat in order to make it end up right across the river. Well, obviously, if I want to end up straight across the river, I need to head my boat up the stream somewhat. And so if this is the direction I head the boat, that's going to be the speed of my boat in still water, and then it's going to be pushed back to where I wanted it to go with the speed of the current. So your task is to calculate this angle theta to find out how far upstream or what angle upstream you need to head the boat. And so this is going to be pretty easy. This again is a right triangle. Notice that's where your right angle is. So for this theta that I'm looking for, I know the side opposite and I know the hypotenuse. Opposite and hypotenuse would be sine, and so the sine of theta is equal to BC over BB. And therefore theta equals inverse sine of the speed of the current divided by the speed of the boat. Now, if I want to know how long it's going to take me to get straight across the river, straight across, I need to know the actual velocity, because that's the straight across velocity, and the straight across distance, 65 meters, is what I know. So let's see how we can go about finding the time. Find the time to go straight across. Well, I'm going to need to know V actual. That's one leg of the triangle. And so using the Pythagorean theorem, BB squared equals VC squared plus V actual squared. So V actual will be equal to the square root of the speed of the boat in still water squared minus the speed of the current squared. That would give you your actual velocity. Then to find the time, we'd say V actual, after you've already calculated what it is equal to the width of the river, because that's the straight across distance. And if I'm using the straight across velocity, I use the straight across distance over the time. Time is in the denominator, so I'm going to multiply through by t, and then I will divide by the actual. So t is equal to the width of the river divided by the actual. So these are two very similar problems, but the end result is different. In this situation, we're trying to end up straight across the river. In the previous example, you were headed straight across the river and got pushed downstream. In order to end up straight across the river, you have to head upstream so that when the current pushes you downstream, it actually pushes you to where you end up straight across the river. And that is that.